In section 1.2, we're going to talk about row reduction and echelon forms. We're going to continue talking about solutions of linear systems and dive deeper into this triangular form that we introduced in section 1.1. The idea of triangular form is going to be generalized into some kind of echelon form. So let's introduce what echelon form is. Sometimes it's called row echelon form, and sometimes this is abbreviated with an REF, row echelon form. So a matrix is in row echelon form if all non-zero rows are above any rows of all zeros. So what this means, and we have three examples of echelon form here. We have some rows of zeros, and those rows of zeros are always the last rows in the matrix. That's what's happening for this first thing. All non-zero rows are above any rows of all zeros. So the idea of this row echelon form is we are doing row operations on a matrix. We are reducing it into an easier form that we can solve the solution, or solve the equation, solve the system. And we get to a form that's simple, and this is the simple form that we're getting to. So all zero rows are at the bottom, non-zero rows at the top. We also need that each leading entry, the leftmost non-zero entry of a row, is in a column to the right of the leading entry of the row above it. So the leading entries of these rows, these are the black boxes here. These are the leading entries. And we can see that these are the leftmost non-zero entries of the row. Everything to the left of them are zeros. That's what we're saying here. Everything to the left of those entries are zeros. And we're saying that those leading entries are going to the right as we're going down the matrix. This is our idea of our triangular form that we introduced in the last section. The triangular form here would be that your leading entries are all on the diagonal and you have zeros everywhere else. Your leading entries are going to the right as you're moving down. Now you can see in this last example sometimes we may skip a couple columns. That's fine, but you do have that we're going to the right. So that is the second thing here. The third thing here is all entries in a column below a leading entry are zero. So that is saying every single black box here, everything below it is zeros. If we have that, then we have this thing called row echelon form. And this is like the triangular form that we introduced in the last section that makes it possible to solve a system of equations. If we have it in row echelon form, we'd be able to back substitute and solve for each variable. The more important thing we're going to look at is something called reduced echelon form or reduced row echelon form. And oftentimes this is abbreviated with RREF, reduced row echelon form. So here, it's the same thing as echelon form, but a couple differences. One, we have that the leading entries are now 1 instead of the black boxes, which means they could be any value. So these are the ones, the leading entries. And we have one other thing, that each leading one is the only non-zero entry in its column. So we have that not only below those leading entries are zeros, but also above the leading entries are zeros. They're the only non-zero value in those columns. Right? It's like echelon form, but we have ones instead of any non-zero value and zeros above those non-zero leading entries, or those one leading entries. What's very special about row reduced echelon form, or reduced echelon form, is that it is unique for a linear system. Now, unique means that this form is correct, but these stars mean that any value could be here. So that's not necessarily unique. You might have different values depending on how you're solving the system, but the overall form is unique, and that's going to be very special for us later on. So we're going to introduce some more terms that in correlation to these echelon forms. That is pivot position, pivot, and pivot column. So a pivot position of a matrix is a leading entry in an echelon form of the matrix. That is the black boxes here, the pivot position. A pivot is the actual value associated with it. So it's a non-zero number that is used in a pivot position. And we're going to understand what that is when we're talking about row reduction. That is, we're going to use that value to create zeros underneath or above to get reduced row echelon form. A pivot column is the column that a pivot is in. And that's going to be important, as we'll see, because the columns are represented by variables in the system. And when we have a pivot column, what we're saying is that there's something special about that variable. Okay, and all of this is true for reduced row echelon form as well. We have our pivots here. Those are the leading entries. And we have our pivot columns associated with those leading entries. Right, so we can think of a pivot as just a leading entry in the row echelon form or reduced row echelon form. Pivot position is where is that located, and a pivot column is the column that it's located in. So let's look at an example. We're going to row reduce the following matrix into echelon form and locate the pivot columns. Okay, once we put it into echelon form, we'll be able to locate the pivot columns. So we start with this matrix, okay, and we're going to do some row operations to get it down to echelon form. The first thing that we're going to look for is that we want a 1 or a non-zero entry in that top leftmost position. In order to have leading entries go down from left to right, it's going to be important to have a 1 in that top entry. So an easy way of doing that is to just switch that row with a row that has a 1. That's why we do this row 1 switch with row 4 here. Interchange the rows, and now we have a 1 in that top leftmost position. This is a pivot. And the idea of a pivot or a leading entry is we are going to use that to get zeros underneath this. We're going to try to zero out these entries. Using the pivot. So one of these is already zeroed out, so you don't have to worry about it. But the -1 and -2 are not. So to do that, we are going to do our common row operation, and that is we're going to take a multiple of row 1, add it to the corresponding row, row 2 or row 3, and make that the new row 2 or row 3. So if I have a -1 here, and I want to get rid of it, well, I just take the opposite of it, which is just 1, multiply that by row 1, and I get row 1 plus row 2 is going to be my new row 2. I take all the entries of row 1, multiply them by 1, don't have to do anything, add them to the values in row 2, and that's my new row 2. And that gives me a 0 right there. Same thing for this -2. I take the opposite of it, that is a +2, multiply it by row 1, add it to row 3, and that becomes my new row 3. If I take 2 times 1 minus 2, I get that 0 right there. All right, so I've now taken this 1, this pivot, zeroed out everything below it, and now I'm going to continue to try to get another pivot and continue that process. So one way to do this is to look at your matrix as you have it now, And you can kind of ignore the top row now and look at the rest of the matrix. And you're going to try to get a pivot in the top leftmost position that you can. That's also going to be ignoring this first column in this case as well. So we're going to try to get a pivot in that position. This is going to be another pivot. And I'm going to undo that. There we go. So a pivot is going to be if we ignore the first row and the first column because we've already zeroed them out, we've had a pivot in that first row, what's the top leftmost entry that I can get? And even though we can work with this as a 2, it's going to be easier to work with it as a 1. So let's make this a 1. And that's where this 1/2 row 2 into row 2 comes from. And now I have my pivot as a 1. I'm going to try to zero out the entries below it. Using the pivot above it. And to do that, same process I did before, take the opposite of the value, multiply it by the row with the pivot, and add it to the row that we're trying to zero out. And that's our new row. So -5 times row 2 plus row 3 would be our new row 3. 3 times row 2 plus row 4 would be our new row 4. And we get this matrix out when we do this. We can see here our pivot with everything zeroed out underneath it, our pivot with everything zeroed out underneath it, and then we have a bunch of zeros as well. One thing we need for row echelon form is that we need this 0 row to be the last row in our matrix. So I'm going to interchange row 3 and row 4 so that that's the case. And when I do that, I am now in row echelon form. Pivot here, pivot here, pivot here. I could make that a 1 if I wanted to, but in echelon form it doesn't really matter. So these are the pivots, which means that my pivot columns are the first, second, and fourth columns. One thing that's going to be important is this last remark right here. There is no more than one pivot in any row or column. You can't have 2 pivots in one row or 2 pivots in one column. All right, that's going to be very important going forward. That's from the definition of row echelon form, how it works out. But you can only have one pivot in each row and each column. So next example here, we're going to row reduce this matrix to echelon form and then to reduced echelon form. I want to make it clear that when we bring it into echelon form, we are able to get information that's going to be helpful to us, but in order to solve a system, we're going to get it down to reduced echelon form, which is some extra steps that we have to take. So echelon form is nice because we can get some information very quickly, but really to solve a system, we have to take it one step further. So here we go. We have this matrix. We're going to use these little squiggly lines, this similar thing, to mean that these matrices are row equivalent. You can get from one matrix to the other with some row operations. We're not going to go over what those row operations are in this example. You can go through them in your own. For instance, the first row operation is swapping row 1 and row 3. And we're doing some zeroing out. And you could go through and identify what those row operations are. But in this case, we're not going to get to that point. All right, so if we go through those row operations, we're going through all of them. We're trying to get a pivot in this top left column. We're trying to zero out the entries below it. Trying to get a pivot in this next top left entry if we ignore the first row and first column. And we're going to try to get a 0 underneath it. And when we do that, we get our final echelon form. We have our pivots. They move from left to right as we go down. Zeros underneath. They don't have to be ones necessarily. This is our echelon form. We can see right now our pivot columns are 1, 2, and 5. Those pivot columns are not going to change as we go to reduced echelon form. All right, to create reduced echelon form, we're going to create ones in the pivot column. We're going to try to get zeros above it. So we're going to work from the bottom up. It's not necessary, but I think it's useful here. Looking at our pivot, it's a 1, and I'm going to try to zero out everything above it using those same row operations. So this would be negative row 3 plus row 2 is our new row 2, and negative 6 row 3 plus row 1 would be our new row 1. That would zero out those two entries, get us a new row 1 and row 2. Pivot, zero out the stuff above it. We're going to do that for the next pivot as well. We have our pivot. We're going to try to zero out what's above it. Again, that row operation would be 9 row 2 plus row 1 into row 1. We have our pivots. We have our zeroed out entries above. And then finally we have our last pivot of 3. And we just want to create that into a 1. So we take 1/3 row 1 into row 1. We have our 3 pivots here. They're in the same echelon form, and this form allows us to solve for the system in a nice, easy way. Before we can talk about really solving that system, we need to talk about the different kinds of variables that we introduce in this section. That is a basic variable and a free variable. And the difference between them for us is going to correspond to the pivot columns. The columns are all represented by variables. So let's just make sure that's clear. The columns represent variables. Some columns are going to be pivot columns. Those are going to be the basic variables. And the other ones are going to be free variables. So pivot columns are going to be the basic variables. Non-pivots are the free variables. That's all we're saying right now. All right, so we have this reduced row echelon form matrix in this example. We're going to identify what the pivot columns are, the basic variables, and the free variables of the system. So our pivots here are this one, and this one right here. You can see that there's zeros underneath them, and zeros above them. That means that we're in reduced row echelon form. Reduced row echelon form. And the pivot columns here are the columns that are associated with those pivots. That is column 1, column 3, and column 5. Which means that our basic variables are the variables associated with those columns. That's going to be x1, x3, and x5 in the original system. Right? Our x1, our x3, and our x5 in the system. The free variables are the other ones. That's our x2 and x4. That's our free variables. Noting that the last column is in the augmented matrix. That's just going to be a bunch of constants. There's no variable associated with that last column. Now that we have these basic and free variables and we have this row-reduced echelon form, now we can solve this system. So here in this example, same example as we had before, we have our same system, we have our basic and free variables. We are going to write the basic variables in terms of the free variables, if there are any. So our basic variables here are x1, x3, and x5. And we are going to write those basic variables in terms of our free variables, x2 and x4. We get those solutions just from the equation. So we have x1 plus 6x2 plus 3x4 equals 0. We are just subtracting 6x2, subtracting 3x4 on the other side, and getting an equation with x1 on the one side. Same thing with the other two equations. We have this x2 is free and x4 is free. Note that sometimes we're going to write that as x2 equals x2 and x4 equals x4. So what we're really doing here for a general solution is we have our 5 variables. This is how we're always going to do a general solution here on the left-hand side. And then everything over here is going to be written in terms of the free variables and or constants as well. So you're going to write all the variables in terms of the free variables and or constants. x1 is negative 6x2 minus 3x4. x2 is equal to x2, free variable. x3 is 5 plus 8x4, free variable. x4 is equal to x4, free variable. x5 is equal to 7, no free variable, but just a constant. So why is this called a free variable? Well, the idea is that x2 and x4 can be any value, and this solution is still satisfied. So x2 and x4 can be any value, and there is still a solution to the system. That means that there are infinitely many solutions when we have a free variable. The free variables act as parameters. This is a parametric description of the solution set. The parameters can be any value, and when I pick a certain value, that gives me a new solution. So for example, let's say that x2 was 1 and x4 was 0. That's just two choices. Then in that case, x1 would be negative 6 times 1 minus 3 times 0 minus 6. x2 would be 1. x3 would be 5 plus 8 times 0. That's 5. x4 would be 0. And x5 would be 7. So my solution would be negative 6, 1, 5, 0, 7. Now, there is nothing special about the choices I made for x2 and x4. I could have chosen any real numbers, and that would give me a new solution. That's why there are infinitely many solutions. One thing to keep in mind here is that we are only going to use the reduced echelon form to solve a system. The echelon form is helpful. It allows us to quickly see what the pivot columns are. That is, we can see what the free variables and basic variables are. We are also able to decide if there are infinitely many solutions or unique solution or no solutions, but in order to solve the system, we're going to put it into reduced echelon form. Okay, and this is again our question of existence and uniqueness. Existence, is there a solution? Is the solution consistent? Uniqueness, is there one solution, or are there infinitely many solutions? So in this example, let's determine if the following system is consistent, and if so, if there is one unique solution or infinitely many solutions. So here's our system. We put it into our matrix, and we put it into echelon form. This is our previous example that we worked on. Just from this point, just from the echelon form, row echelon form, we can see if there's going to be no solution, one solution, or infinitely many solutions. All right? Because I don't have an equation like 0 equals c, that's going to be something of the form zeros and then some value at the end c, where c is non-zero. Because I don't have that, then there is a solution. But because I have free variables, call these free variable columns, because I have those, x3 and x4, then I have to have infinitely many solutions, because those free variables can be any value. So a quick handy thing to remember is if you have a consistent system with free variables, there are infinitely many solutions. Right? In order to find those solutions, or find a parametric description of the solutions, you need to put this into reduced row echelon form. But we can just see that there are infinitely many solutions right now. All right, another example here. Determine if this is consistent, and again, if there is so, is there one unique solution or infinitely many solutions? I take this system, put it into the augmented matrix, put it into echelon form. Again, this is row echelon form. All right, I can see my pivots here. I have no free variables. There are no columns, except for that last one, or including that last one as well, that have a pivot, or that don't have a pivot. All right, it's okay that we have this row of zeros. All right, and we should say that a row of zeros does not give us a lot of information. As we get more comfortable with this, it does give us some information, but really we cannot say that a row of zeros means infinitely many solutions. A row of zero means this or that. In this case, we have a row of zeros, but we have a consistent system with no free variables. There is one unique solution here. We could find that unique solution. We have 3x1 plus 4x2 is equal to negative 3. And there should be a space here. And we have x2 equal to 3. If I plug in that x2 equals 3 above, I have 3x1 plus 4 times 3 equals negative 3. That is 3x1 is going to be equal to negative 15. x1 equals negative 5, and my solution is negative 5 comma 3. Okay, I don't have the row with zeros and then a non-zero after the equal sign. And I don't have any free variables, so it is one unique solution. And that's what this theorem, existence and uniqueness theorem, is talking about. A linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. Right? This would only be a pivot column if this lastmost entry is non-zero and everything to the left of it is 0. A linear system is consistent. If a linear system is consistent, then the solution contains either a unique solution when there's no free variables or infinitely many solutions when there's at least one free variable. This theorem is just talking about the last two examples that we did and saying that this is true always. So let's talk about our strategy for solving linear systems. When we have a system, first thing we're going to do is we're going to write the augmented matrix of the system. We're going to use our row reduction algorithm using our 3 row operations to obtain an equivalent matrix in echelon form. Row echelon form. From this point, we can decide whether the system is consistent. If there is a row of zeros with a non-zero entry at the very end, there's a pivot in the last column, then we can stop. We know there's no solution. We don't have to go any further. And we can decide actually at that point if there are free variables or not. But we do have to continue and get to reduced echelon form, reduced row echelon form, to actually solve it. We write the system of equations corresponding to the matrix obtained in step 3. And then we are going to express the basic variables in terms of the free variables and declare the free variables as well. And that gives me a parametric description of the solution. I can plug in any values for those free variables and get a new solution out. So last thing in this section, let's talk about some examples about the number of free variables that I have, the number of pivots that I have. So what is the largest number of pivots in a 4 by 6 matrix? It's important to understand that we're talking about 4 by 6 matrix. We are saying that there are 4 columns, or 4 rows, and 6 columns. 4 by 6, that is rows by columns. So what is the largest possible number of pivots that a 4 by 6 matrix can have? And it might be good to kind of pause the video and just sort of explore for yourself what could that be. There was one point that we said that there has to be at least, or at most, one pivot in each row and each column. So because of that, I can only have 4 pivots. They could be in different spots, but that is the most that I could have, 4 pivots. Same thing for a 6 by 4 matrix. A 6 by 4 means you have 6 rows and 4 columns. But since each column can only have 1 pivot, the most you could have is 4 pivots as well. Now you might be skipping some rows. That actually just means that you have some 0 rows at the end. But again, the answer is 4 pivots. All right, next thing. How many solutions does a consistent linear system of 3 equations and 4 unknowns have? All right, if there are 4 unknowns, that means we have 4 columns before the augmented part of the matrix. If there are 3 equations, that means there are 3 rows. 4 unknowns means that there are 4 columns plus the augmented column. So it's going to be a 3 by 5 matrix. Three equations, 4 variables plus the augmented column equals some constants. So the question is, how many solutions does this have? Well, this is consistent which means that we cannot have something like at the end zeros plus some non-zero number there. We cannot have that. So no matter where our pivots are, we have to have a free variable. There are not enough pivots to cover the 4 unknowns. There has to be a free variable. And that means infinitely many solutions. Okay, and you can play around with that. Try to create the pivots so that every column does have a pivot. The 4 variables do, but you will never be able to get it unless you have some kind of inconsistent system. All right, last thing. Suppose the coefficient matrix corresponding to a linear system is 4 by 6 and has 3 pivot columns. How many pivot columns does the augmented matrix have if the linear system is inconsistent? So one thing we're talking about here is the coefficient matrix is 4 by 6, and the augmented matrix is 4 by 7. There's one extra row there or one extra column that we have there. So in the coefficient matrix, we have 3 pivot columns. Who knows where they are? There's 3 pivot columns. If the linear system is inconsistent, then that means that the last row has to be something like this, where we have zeros to the left of it, left of that equal sign, and then some non-zero value in the last one. And then we can see that this is a pivot. And this is another way to describe an inconsistent system, is that there is a pivot in the last column, in the augmented column. So how many pivots does the augmented matrix have? The answer would be 4 pivots if there are 3 pivots in the coefficient matrix, one more pivot.